Hello students, let us learn the Fourier cosine transform evaluation in this video. So let us consider one example. Find the Fourier cosine transform of f of x is equal to 1 upon 1 plus x square. So here we'll use the definition of Fourier cosine transform, which is denoted by fc of s. So fc of s, it is equal to integration from 0 to infinity f of x cos sx dx. Let us substitute f of x. F of x is 1 upon 1 plus x square. So we have fc of s is equal to integration from 0 to infinity 1 upon 1 plus x square cos sx dx. Now this integrand cannot be integrated easily. Hence, we go for differentiating the whole equation with respect to s. Derivative of f of s, it is f dash of s. RHS is an integral, so we go for using the Leibniz rule of differentiation under the integral sign. So what it tells us, we have to differentiate the given term with respect to this parameter s by going for partial differentiation. So let us keep 1 upon 1 plus x square as a constant term. Differentiation of cos sx with respect to s partially. It is minus x into sine sx. Now this term or this integrand again cannot be integrated easily. Hence, we'll go for multiplying and dividing the function by x, and minus is kept outside. So it becomes x square sin sx divided by x into 1 plus x square, which again cannot be integrated easily. Hence, again we go for adding and subtracting 1 for x square term. Add and subtract 1 for x square term, and then split this integral as sum of two integrals. So we'll take 1 plus x square into sin sx divided by x into 1 plus x square as one term with minus sign outside. Now for the second term, it is minus 1 into sin sx, and outside we have one more minus, so it becomes plus integration from 0 to infinity of sin sx divided by x into 1 plus x square dx. Now here uh, 1 plus x square term cancels. We are remained with sin sx divided by x in the first integrand. Second integrand is kept as it is. Now we know that integration from 0 to infinity sin sx by x dx, it is minus pi by 2. And second integrand, again this cannot be integrated easily. So what we do is again go for differentiating with respect to s. So derivative of f dash of s, it is f double dash of s. Derivative of constant is 0, and here we have again we will go for the partial differentiation of the term sin sx, which is x cos sx, and 1 upon x into 1 plus x square is treated as a constant term. Now x cancels off here. Now we are remained with integration from 0 to infinity cos sx divided by 1 plus x square dx, which we can see from equation 1 is nothing but fc of s. So this integral will write it as fc of s. Now take it to the LHS. It is f double dash of s minus f of s is equal to 0. Now we need to solve this differential equation. Now to solve this differential equation, we'll write it as d square minus 1 of f of s is equal to 0. The auxiliary equation is given by m square minus 1 equal to 0. The roots of the auxiliary equation are m equal to plus or minus 1. Now the complementary function itself becomes the solution here, and the solution is therefore written as fc of s is equal to c1 e raised to s plus c2 e raised to minus s, because the roots are real and distinct. Now this does not end the solution. We need to find the values of c1 and c2. For that, let us put s equal to 0. If we put s equal to 0 in equation 3, so it becomes fc of 0 is equal to c1 e raised to 0 is 1, again plus c2 e raised to minus 0 is also 1. We are remained with fc of 0 is equal to c1 plus c2. Now what is this value of fc of 0? For that we go back to the equation 1 here. In this, if you put s equal to 0, we get fc of 0. Now, if you put s equal to 0 here, cos 0 is 1. So, we are remained with integration of 1 upon 1 plus x square from 0 to infinity. So, that term is considered here. fc of 0, it is integration from 0 to infinity 1 upon 1 plus x square dx. Integration of 1 upon 1 plus x square is tan inverse x integrated between 0 to infinity. Now tan inverse infinity is pi by 2, tan inverse 0 is 0. So we get the value of fc of 0 as pi by 2. Substitute it here. We get pi by 2 is c1 plus c2. Let us call it as equation 4. Now since there are two constants, we need two equations to solve them. So let us differentiate this equation 3. So with respect to s here, so we get f dash of s is equal to c1 is constant, derivative of e raised to s is e raised to s minus, because derivative of e raised to minus s is minus e raised to minus s, c2 is again constant. Now again we'll go for substituting s equal to 0. If we put s equal to 0, we get f dash of 0 equal to c1 minus c2, because e raised to 0 is 1. Now we have to find the value of f dash of 0. Now for that again we go for the previous result. This f dash of s is equal to, we have this. If you put s equal to 0 in this equation 2, the integrand totally reduces to 0 and we have f dash of 0 is equal to minus pi by 2. So this value from equation 2 will be substituted here. So we get minus pi by 2 is equal to c1 minus c2. Now we have got two equations, equation 4 and equation 5, which we need to solve for c1 and c2. Now if you add these two equations, c2 cancels and even pi by 2 on the LHS cancels. We get 2c1 equal to 0 or c1 equal to 0. Now, if you subtract these two equations, equation 4 and 5, that is 5 is subtracted in 4, then pi by 2 minus of minus, it becomes plus pi by 2. That is 2 times pi by 2. Now, if you subtracting c1 from c1, then it becomes 0. Then c2 minus of minus c2, it becomes 2c2. But 2 cancels from LHS and RHS here. Now we have pi by 2 is equal to c2. Now we got the two results. C1 is 0, C2 is pi by 2. Substitute them in our result, that is equation number 3. So we have the result fc of s is equal to C1 is 0, C2 is pi by 2. It is pi by 2 into e raised to minus s. So that is the Fourier cosine transform of the function 1 upon 1 plus x square. Thank you for watching.